So this is quite an interesting question. Let's say that this is a brand new computer, fresh out of the box, that's never been used before, and you plug it into a brand new network that's never been used before, and you open up the web browser, and you type in google.com, and you click on enter. What actually happens next in detail? What you might say is that the client's going to go ahead and generate an HTTP request destined to the google.com servers. That's going to go to google.com, at which point Google's going to answer with an HTTP response and then relay that back to the client. And you would be correct. That is what's going to happen eventually, and that is how HTTP traffic works. But that's actually going to be the very last thing that happens from the moment you go to your browser and type in Google and click enter. It's going to be the very last thing that happens before the google.com website is actually rendered in your browser. There's going to be a whole lot of traffic that's going to happen before that. And most of it's actually going to be cached, which is why in this example, we're going to assume we're using a brand new computer on a brand new network. And we're going to go ahead and run through in detail every single thing that happens before your computer is actually able to reach Google. So we take this brand new computer, fresh out of the box, and we plug it into a network. This is just a regular layer 2 switch. This is just a regular router, like the home router within your home network that we use to reach other devices on the internet. In this case, this is going to be a DHCP server, which is going to come in handy later. And this is just another regular computer, same as this computer on your network, just so we can illustrate some concepts. So you take the computer, you plug it in, and the very first thing that happens actually is going to be some layer 1 link negotiation. Now, layer 1 just refers to the physical link itself. In this case, we're going to say we're just using Ethernet, but this applies to other types of links as well. Layer 1 just refers to the general physical link and traffic relating to that link. And automatically, the moment you plug it in, both the link speed, which could, be like 1 gigabit per second, 100 megabits per second, the link speed is going to be automatically determined by the link. And the duplex is also going to be automatically negotiated. Duplex just refers to full duplex, lets the PC send and receive traffic over the link at the same time. And half duplex means the link can only be used to either send traffic in one direction or the other direction at the same time. That just happens automatically the second you plug it into the network. There's not a lot to worry about there. Now, the second thing that's going to happen is the PC at this point in time doesn't actually have an IP address. We know that in order for the PC to communicate with Google, it's going to need to assign itself an IP address somehow. One way is that the human could actually go on the computer and open up command prompt or control panel or whatnot and actually statically assign an IP. But most of the time, whether it's the same thing, even if it's a phone over Wi-Fi or a computer over Wi-Fi or Ethernet, is you never actually need to do that before because we have a protocol called DHCP, which stands for Dynamic Host Configuration Protocol, that's responsible for assigning an IP address to the computer automatically. And this is the DHCP server that has a pool of available IP addresses, and it leases them out to devices on the network. So the PC now is going to go ahead and realize it doesn't have an IP address and it needs one, and it's going to initiate a 4-part DHCP handshake. The first thing it's going to do is it's going to generate a DHCP discover message, which basically is going to, for addressing, we're using MAC addresses here. You can think of this as layer 2 addressing. Layer 2 uses link local or MAC addresses, also called burned in addresses. Those just come burnt into your computer's physical NIC, NIC, network interface card, and you don't really get a say. Those just come from the factory. And every single piece of layer 2 traffic, or actually every piece of any traffic, is going to have a layer 2 header in that traffic, which is going to have both a source MAC address, which is the PC that generated it, and a destination MAC address, which is the device that the packet is being sent to. Later on, once the PC has an IP address, we're also going to start seeing layer 3 headers, which use IP addresses for global routing, but MAC addresses are called link local addresses. They generally stay within your network. So in this case, we're going to say that the PC comes from the factory. You don't really get a choice, with a MAC address of, let's just call it AA:AA. Of course, in real life, the MAC addresses are going to be longer. We're just going to abbreviate to make things simple for the video. So we're going to write down a source MAC address of AAAA, since it's coming from the PC. And the destination MAC address is interesting. The PC needs to reach the DHCP server, but the PC, of course, doesn't know the MAC address of the DHCP server. So there's a special MAC address, which is essentially just all Fs, which is the broadcast MAC address, which essentially gets sent to every single device on the network. That's what a broadcast is. And there's also layer 3 broadcasts as well, which we'll see shortly. But this is how it works for the DHCP discover message. The PC is now going to send this out of the PC as a host, so it's only ever going to be plugged into one device at a time. And this DHCP discover is going to come to the switch. And the switch is going to do a couple of different things. Firstly, it's going to go ahead and read the destination MAC address and see all Fs, and it's going to know that it's a broadcast. So it's actually going to do something called flooding. If this were to be a single MAC address, it would do something called forwarding, where it sends it off to one device. But because it's all Fs, it's a broadcast, so it's going to flood it. So it's going to go ahead and send it out of this port, out of that port, and out of that port. It sends it out of every single port besides the port that it was received on, just because, of course, that would be redundant. But now, while it does that, now the other two devices are not DHCP servers. They're going to read that this is a DHCP discover, and they're just going to discard it. The DHCP server is going to do some further stuff with this packet, which we'll see in a minute. But so the switch is responsible for either forwarding or flooding, but it's actually going to do something else. So the switch actually has something called a MAC address table. And what that does is that's just going to be a mapping between MAC addresses and the port on the switch physically that the device is plugged into. So because the switch received this packet on this port, in this case, we're just going to go ahead and call this port 1. Let's just call it P1 for port 1. Because the switch received this packet, it would have read the source MAC address of AAAA and knew that now there's a device with that MAC address plugged into port 1. So what that's going to look like is we're going to say that this quad A MAC address is now going to be associated with, in this case, we're just going to call it port 1. And we're going to see additions happen to this MAC address table later, but that's all it does. So what happens next is the DHCP server now has this DHCP discover message, and it knows that there's a PC with this MAC address trying to get an IP address lease. And what it's going to do now is it's going to go ahead and, assuming the pool is not exhausted, is it's going to offer the PC an IP address. And it's actually going to give some more information, which we're going to see in just a second. But the main thing is an IP address. So the source MAC address can now be changed to the MAC address of the DHCP server itself. In this case, we're just going to say that that's just all Bs. And now because the AAAA MAC address was previously in the source MAC address field, the DHCP server is aware of the exact device to send this DHCP offer to. So it's going to send that to quad A. And now, rather than being called a discover, this is now going to be called an offer. And this is the second thing. And because these are now A's instead of F's, just being a specific MAC instead of that special all F broadcast MAC, this is now going to be called a unicast rather than a broadcast. This is now going to be sent back to the switch, and the switch is now going to look into that destination MAC address field, and it's going to see that it's A's, and it's now going to do a MAC table lookup and see that the MAC address that's all A's is bound to port 1, so it doesn't need to now flood it out of every single port like it did before. It can now just do something called forwarding instead of flooding and just send that directly back to the PC. And that is what's going to happen, but there's one thing that we missed, is this MAC address table. Since the switch now looked at this packet, it would have looked into the source MAC address field and saw all Bs, and that means that the switch now learned that out of this port, which in this case we can just go ahead and call port 2, it knows that it can now put an additional entry into this MAC table. And it's now, in this case, going to take that source address of all Bs and bind that to port 2. So this is now the state of the MAC address table is going to look on the switch, and the PC would have received this DHCP offer. So we're halfway done the DHCP handshake. Just for the sake of time, we don't really need to worry about the other two packets. The other two packets, the acronym for DHCP is actually known as DORA, D-O-R-A, which stands for DHCP discover, DHCP offer, DHCP request, and then DHCP acknowledgement. The reason why we have the R and the A is there could have been multiple other DHCP servers on the network that could have sent the PC different offers. Now that the PC has an offer, it technically needs to send a request confirming that it is choosing to accept a specific offer, and the DHCP server will finally acknowledge. It's basically just a confirmation process. We don't really need to worry about the specifics of that. It's just good to know that that happens. So within this offer now, there's going to be a bunch of information that the DHCP server would have given to the PC. So from this offer, which is now the data from that offer the PC now accepted, it would have got, in this case, we'll say 4 pieces of information. The main thing is the PC now would have got an IP address. So 192.168.110 is now assigned to this PC, so it's now able to communicate over the open internet. It also would have gotten a subnet mask, which essentially just lets the PC know which devices are on the PC's own network and which devices are outside of the PC's own network. Without going into too much detail, these 3 being 255 essentially just mean that these first 3 octets are essentially just the network portion, and then the last octet being this 10 is the host portion, which means that 192.168.1, let's say, 12, the PC knows is on its network, whereas let's say if this bit changes, now it knows that this address is not on its network. That's really all that means. I might make a video later on, more advanced IP addressing. The default gateway is very important for, let's say, for reaching Google or Netflix or Amazon or any website on the open internet. The PC immediately knows that it needs to contact its default gateway. In this case, that's going to be this device over here. In a home network, it's just going to be your router, which is the default gateway. So the DHCP server needs to let the PC know if you're trying to reach a website that's outside of your network, you need to go ahead and first reach out to your default gateway, and the default gateway will perform routing from that point on. And then lastly, it would have given a DNS server, which we're going to see in a moment. A DNS server is just the mechanism in which a PC can actually resolve a host name, such as google.com, to the underlying IP address. So everything at this point in time would have happened automatically in real time, just a couple of seconds after you plug the PC into the network. Now let's say use the human, actually go to your browser, you type in google.com, you click and enter. What's actually going to happen now? Well, the PC is going to go internally into its own DNS cache, and it's going to go and see, do I have any cache data for google.com? We need to actually resolve google.com into an IP address. Of course, there's nothing cached yet. So it's going to need to know that it's going to need to send a DNS query to a DNS server. In this case, we're just going to call this the DNS server, which has an IP address of 192.168.1.200. Now, the issue is you might think, let's say we have a packet here. I'll say what an ARP is in a second. But if the PC were to go ahead and send that DNS request directly to the DNS server, we know what the source and we know what the source and destination IP address would be, but we don't actually know what the destination MAC address would be, right? We know what the source address would be is all A's, but we don't actually know how to actually address the layer 2 MAC address of the DNS server since there's nothing cached yet. So to do that, we're going to need to send out a special type of traffic before we actually do DNS traffic, which is called ARP, which stands for Address Resolution Protocol. What an ARP is it basically just tries to resolve an IP address to a MAC address, right? So for an ARP, same as always, the source MAC is going to be all A's, and the destination MAC is actually going to be all F's, which if you remember is a broadcast because we don't actually know what the MAC is. We're trying to figure it out. And then with the ARP, we're now getting in more into the range of layer 3 traffic. So in addition to the MAC addressing, which is the layer 2 header, we're also going to start to see things that are layer 3 headers or are close to resembling layer 3 headers. In this case, we know that the source IP address is just the IP address of this computer. We're just going to write 110, assuming that, it's just prefixed with 192.168. And then the destination IP address, we actually do know what that is it's going to be 192.168.1.200, since the PC is now aware of which DNS server to contact, since the DHCP server gave it that information. So this now is called an ARP packet, and that's going to now be sent out to the switch, and the switch is going to go ahead and do a lookup, and it's going to see the destination MAC is a broadcast, so it's going to flood it out of every single port besides the port it's plugged into. The other two devices are just going to discard it because it's not needed at the moment. Because the second thing that's going to happen, technically once it reaches all 3 devices, is the destination IP address is going to be looked at. In the process of decapsulating all of those layer 2, layer 3, layer 4, up to layer 7 headers, going through that process is called decapsulating. So they're going to be decapsulated technically on all 3 devices, and the thing that they look for is that destination IP. They only essentially are going to be interested in the traffic if the destination IP address is their own IP address. If it's a different IP address, they can safely discard the packet since the traffic was not intended for them. The switch in this case is a layer 2 switch. The switch is not going to do that. There's other devices that can do that. So in this case, it's going to reach the DNS server, and it's going to do the decapsulation, and because it has the IP address of 1.200, it knows that it is the device that the PC was trying to ARP for, and it's now just going to go ahead and answer with its own MAC address, right? So the source MAC address is going to be the MAC address of the DNS server itself. In this case, we're just going to say that that's just all C's, and in this case, it can go ahead and send that back directly to the PC. The source IP address, of course, we know is going to be 1.200 since it's coming from the DNS server, and this is now destined to the PC. It essentially just takes the source and destination and just flips them around. So we can fill this out with destination IP is just going to be 1.10, and it's now going to send this back over here. And now this layer 2 switch is going to look at this, and it's going to see that the destination MAC is AA, and it's going to send it over to the PC. And the PC now knows that the source MAC address for the thing that it ARP for, which is this DNS server, is all C's. But of course, because the switch now received another stream of traffic, it's going to go ahead and update its MAC table. So now it knows that, let's say that this is called port 3. It now knows that we have a MAC address consisting of all C's directly connected to port 3. So now the PC knows the physical MAC address for the DNS server, which is all C's. So that's all the ARP is. The ARP just consists of one single ARP request and one single ARP reply. And the PC is now going to start building a cache of its own, known as an ARP cache. And that's just going to be an IP address to MAC address mapping. So it knows that, let's just say 1.200 is now going to be bound to CCCC. And this now, ARP cache is going to be existing on the PC. And technically, these are going to exist on all the devices, but we're going to keep things simple and just look at things from the perspective of the PC. So we can go ahead and speed through some of this, just because it's probably getting somewhat mundane. But what happens next is the ARP was just the prerequisite to be able to reach the DNS server. So now we know that the PC is going to go ahead and use its own source MAC address, and the destination MAC is CCCC, which it just learned. Same thing, that's going to be 1.10, and the destination IP address is going to be 1.200. So this now is a DNS query, which we don't need to pay attention to the details now, is going to flow to this server. All of this information is going to be reversed. The DNS server is going to give this packet back to the PC. And essentially, all of that was basically to resolve the google.com hostname. So what that means now is the PC is actually going to start building a second cache of its own. And this now we can call a DNS cache or DNS table. I've seen it referred to as both ways. And what this is going to be is this is going to be a cache that basically maps DNS names to IP addresses. So if we went to our browser and we typed in google.com, that's what we would have requested or queried from the DNS server. And let's say that the answer that the DNS server gave us is just 1.2.3.4. Just as an arbitrary example, we're going to say that that's Google's IP address. And the PC is now going to hold onto this in its own cache. So any subsequent times we need to go to google.com, we don't need to keep on doing a lookup from the server. The PC can just go into its own cache internally. Basically, every single piece of traffic that we saw so far is being cached. And again, that's one of the reasons why networks tend to be so fast, is almost everything's cached. So now comes the interesting part. The PC now, before it can go and do the actual HTTP traffic, it's going to need to move up into layer 4 territory, which in this case for web traffic we use TCP. And it's going to go through the TCP handshake. I won't show the entire thing. It starts off with a SYN, and then a SYN-ACK, and then an ACK, and same as you've seen before, anything you really just need to understand once, and everything else just happens in reverse. But to send this off, we know that we're going to be using now Google's IP address is the IP it's going to be bound to, or destined to, which is 1.2.3.4 in this case. And anytime the PC generates traffic, it looks at the IP address that it's sending the traffic to, and it looks at its own IP address, and it looks at the subnet mask, and it basically needs to use those three different pieces of information to determine, am I sending traffic to a device on my own network, or am I sending traffic to a device outside of my own network? In this case, the PC knows that if it begins with 192.168.1, it's inside of its network, and if it doesn't, it's outside. And in this case, we can clearly see that this device is not in the PC's network. It's somewhere out on the open internet. So in this case, we're actually going to need layer 3 routing. Anything with the MAC addresses that we saw, the layer 2 switch is good enough, but anything outside of the PC subnet, we're going to need this layer 3 router for. So because we know that google.com is not within our own network, we need the router, and that means that the destination MAC is actually going to be the MAC address of the router. Basically what happens is as packets are routed through the open internet, the source and destination IP address field never change. I mean, they actually do change if you go through a NAT, which is a different story. But in general, they tend to persist, but the MAC addresses are actually swapped out hop over hop, every single layer 3 hop, every single time the packet goes through a router. Because these are hardware addresses, essentially every physical device it touches, if it's a layer 3 device, the MAC address needs to be swapped out. This first hop is from the PC to the router, so we're going to need to fill this in with the destination MAC address of the router, which unfortunately we don't know. We only know the default gateway's IP address, not MAC address. So we're actually going to need to go through the ARP process again. Of course, I won't outline the entire thing, but we know that at the end of that ARP process, we would have a second row in this table, basically mapping this time 1.1, which is the default gateway, to we're just going to say the MAC address of the gateway is just all Ds now. So now we have two things in the ARP cache, assuming a whole second ARP process happened. And at this point in time, we can go ahead and fill in the source MAC address of the PC, the destination MAC address now of the default gateway. And this, of course, stays as Google. And the source IP address is, of course, going to be 1.10, which is going to be delivered all the way to Google. And that's how Google's going to be able to answer us. Technically, there might be some natting going on, but we don't need to worry about nat in this video. I actually covered a little bit of that in my UDP hole punching video if you're interested in taking a look. And then there's one thing we missed is during that ARP process, what would have happened is on the way back with the ARP reply, when the router responded to let the PC know that it's at quad Ds, is again, you guessed it, there would have been another entry into this table, now mapping all Ds to, in this case, we're just going to call this port 4. So let's go ahead and we're going to call that port 4. So finally, at this point in time, all of the caching that needed to be done is now finally done. We got both the ARP cache, the DNS cache, and the MAC address table. And of course, these devices also have their own ARP caches and whatnot. And this TCP SYN will now be sent to the router, the layer 2 switch. The switch is going to see the destination map. Destination MAC is quad Ds, which it already knows is connected out of port 4. That's now going to be sent over to the router. And at this point in time, we now finally leave our own network and we finally leave layer 2 MAC address territory. And we now enter layer 3 routing territory. Obviously, I can make a bunch of videos on routing. It's very complex and very out of the scope of this video. But all you need to know is that this will finally reach Google, the Google server, which is outside of my slide here. And then the Google server is going to do the same thing, where the Google server, not the router, but the Google server, the MAC addresses you don't need to worry about since those will be all different as soon as it leaves that first hop. But the source IP address is now going to be 1.2.3.4 once it reaches the Google server, and the destination IP address, assuming in this case there's no NAT, even though there probably would be, would just be 192.168.1.10, which is of the PC. And that's going to be relayed all the way back to the router, and that's going to make its way all the way back to the PC. And now you're going to need both a SYN ACK and an ACK for the TCP tunnel to come up. And then finally, once all of that is done, even once that layer 4 TCP connection is established, now we're going to have our HTTP request, which the PC, again, everything's already cached. Then we'll send that over to Google. Google will send back the response. And then finally, the PC can now actually receive the HTML and JavaScript and CSS and whatnot for the google.com homepage. So yeah, that's really all there is to it. There's quite a lot of traffic, but it all tends to be very simple. If you want any more videos related to networking at all, I was a network engineering major in university, and I'm doing computer science now grad school. So any concepts at all, let me know. I'd be happy to make a video for them. I thought I'd try something different this video by just doing, I guess, like a not scripted video. Hopefully I'll get better at talking shortly. But yeah, that's all there is. So as always, thanks for watching.